Imagine a world where machines don't just follow instructions, but learn from experience. They don't just compute. They think. This isn't science fiction. It's cognitive computing, where artificial intelligence starts to mimic the way our brains process information. But how does this happen? How do these networks simulate thought, memory, and even creativity? The answer lies in neural networks, massive webs of artificial neurons that process data in ways that surprise even their creators. It's not just about speed or power. It's about the ability to make sense of the world, to adapt, and to evolve. So, what exactly are we talking about? Cognitive computing is the umbrella term for systems that mimic human thought processes using data and algorithms. It's not just about processing data. It's about learning, reasoning, and making decisions. At the heart of this is the neural network, a system of interconnected nodes that process information in layers, much like neurons in the brain. These networks learn from data, improving their accuracy over time through a process called training. Neural networks are not just theoretical. They're already powering everything from image recognition to language translation. They're the backbone of AI, enabling machines to understand and respond to the world in ways that were once thought impossible. But it's not just about speed or accuracy. It's about the depth of understanding these systems can achieve. They can detect patterns, make predictions, and even generate creative outputs, all through layers of complex mathematical operations. In the next week, we'll dive into how these networks are trained, the role of data, and the challenges in making them truly intelligent. But for now, the key takeaway is this. Cognitive computing and neural networks are not just about processing power. They're about replicating the human mind in code. You might not realize it, but every time you scroll through your phone, a cognitive computing system is deciding what to show you. These systems learn from your behavior and predict what you want next, shaping your online experience without you even noticing. Behind the scenes, neural networks process vast amounts of data in milliseconds, mimicking how our own brains make sense of the world. They're not just for AI assistance, they power everything from search engines to self-driving cars. Even something as simple as voice assistance relies on neural networks to understand your speech, filter out background noise, and respond in a way that feels natural and intuitive. Neural networks are quietly revolutionizing industries, from healthcare diagnostics to financial forecasting. They're not just futuristic tech. They're already shaping the tools you use daily. So, the next time you use a smart device, remember, what you're experiencing is the result of years of cognitive computing and neural network innovation. It's not magic. It's just a lot of clever engineering happening in the background. Back in the 1940s, the idea of a machine that could think started with the invention of the first neural network. It was a simple model, inspired by the human brain, but it laid the groundwork for everything that came next. The 1950s brought more formalization, with Frank Rosenblatt introducing the perceptron. This was a big step, but it had limitations that would become clear later. Still, it was a powerful conceptual leap. The 1990s saw the rise of deep learning. As researchers started building networks with many layers, these models could now recognize patterns in data that were previously hidden, opening up new possibilities for AI. Today, cognitive computing systems use neural networks to understand language, make decisions, and even learn from experience. They're not just models. They're thinking machines that power everything from self-driving cars to virtual assistants. Imagine your brain is a team of tiny workers, each doing a little job to help you think. They pass messages back and forth, like a big relay race, to make sense of the world. Cognitive computing is like building a super smart robot brain, made of millions of tiny workers, all working together to learn and solve problems. Neural networks are like a big group of friends who learn from each other. They start with basic ideas, and over time, they get smarter by sharing what they know. Each tiny worker in a neural network is like a little detective, looking for patterns in the world, and getting better at solving puzzles every time it tries. So, cognitive computing is like building a super smart brain, And neural networks are the way it learns, by connecting tiny workers who share knowledge and get smarter together. To start, we need a data set, a collection of labeled examples that the system will learn from. These examples are the raw material that fuels the neural network's training process. The data is then pre-processed to ensure consistency. This might involve resizing, normalizing pixel values, or converting text to numerical representations so the network can process it. Once the architecture is set, the network is initialized with random weights. These weights are the parameters the system will adjust as it learns from the data. Finally, the network is connected to a training algorithm, such as stochastic gradient descent or ATOM, which will adjust the weights to minimize errors in predictions. Once the data is in, the neural network begins processing it through layers of interconnected nodes. Each node performs a simple mathematical operation, like multiplying and adding weights to input signals. These operations are guided by weights, parameters the network learns during training. Weights are adjusted to minimize errors, which is the core of how neural networks adapt and improve. The output of one layer becomes the input to the next, creating a cascading flow of information. This is how complex patterns are built from simpler features, layer by layer. At each step, the network applies an activation function, which introduces nonlinearity. This allows the model to learn and represent more complex relationships than just linear ones. This whole process happens in parallel across millions of nodes, making neural networks highly efficient at handling vast amounts of data and extracting meaningful patterns. Now, the clever twist comes when the neural network starts learning by itself. It doesn't just follow rules, it adjusts its own internal weights based on the data it sees. This is called backpropagation, where the network calculates how much each connection contributed to the final error and tweaks them accordingly. This self-adjusting process is what makes neural networks so powerful. They don't need explicit programming for every task. It's not perfect, but it's smart enough to mimic human-like reasoning and even discover patterns we haven't yet put into words. This self-learning ability is the real magic of cognitive computing. It's not just processing data, it's understanding it. At the core of all this is a fundamental shift in how we model intelligence, moving from rigid, rule-based systems to adaptive, self-evolving structures that learn and grow through experience. These neural networks are built on mathematical principles, using operations like matrix multiplication and activation functions to process and transform information in real time. This is not just computation. It's an orchestrated dance of numbers and logic, where each neuron is a tiny processor working in parallel to solve complex problems. And yet, it's all grounded in something surprisingly simple, the same principles that govern how the brain processes information, reimagined through the lens of mathematics and engineering. This is where the science hums, where the abstract meets the tangible, and where the future of intelligence begins to take shape. Imagine a city where every street is a neuron, and every traffic light is a data point. The city moves without a plan, but somehow it never gets stuck. When the lights change, people follow without thinking, just like a neural network follows patterns without knowing why. It's not smart, but it works. It doesn't think, it just flows, like a neural network processing input and output without ever knowing the difference. This city is a metaphor for how neural networks operate. Not by logic, but by pattern, repetition, and the occasional light switch that changes everything. Before you go, if you enjoyed this, please give it a like and subscribe so you don't miss the next one. And tell us in the comments what you'd like us to make next. We read every single one. Thank you so much for watching. Comment this emoji if you made it to the end.